Log on, tune in, find out. Another good idea from Cambridge.
Shin-ichi Ohta, and we'll speak about Ricci curvature of Finsler manifolds and towards application to Banach space.
Yes, thank you very much. It's my pleasure to give a talk here. And today I will talk about some recent development about Ricci curvature of Finsler manifold and also some possible applications in geometrical balance space. But I'm not familiar with geometrical balance space, and so I'm glad if you have any comments or suggestions. And so the Finsler manifold is a kind of generalization of Riemannian manifold. So okay, so and what kind of generalization? For Riemann manifold, at each tangent space we have inner product. And for Finsler manifold, at each tangent space we have some norm. So this is a kind of natural generalization of Riemann manifold. And then, because we use norm in each tangent space, so I think it's natural to expect just use some connection between Banach space around Finsler geometry. And I will explain some basic things about Finsler geometry first. Finsler geometry. And then talk about some more recent work about Ricci curvature. And then finally I will discuss some possible applications in the geometry of balance space. Okay, so let me start with the definition of Finsler manifold. So the way we consider just connected Riemann manifold, connected Shin-infinity manifold. And then denote by Tm its tangent bundle. And then a Finsler structure is a non-negative function of this tangent bundle. So non-negative function on tangent bundle is a Shin-infinity Finsler structure. So if it's smooth for simplicity, we consider only smooth case, like say f is Shin-infinity, but don't of course expect the zero section. Yeah. So because we consider norms and norms can be very wide at the origin. And the second, we assume homogeneity, but only in the positive definition, positive direction. So we have this kind of homogeneity, but for only for positive sheet. So she is only for positive. Okay. And we also need to assume some kind of convexity. We call the strong convexity. So it's like this. So we assume that matrix defined by it's a kind of Hessian of the square of x is positively mixed. For any non-zero vector things. And here this pi is a coordinate like this. So here the coordinate defined by some coordinate on the manifold. So here xi is some coordinate. Local coordinate of M, and we consider this kind of natural coordinate on the tangent space, and then this is positively. We assume this is positively mixed. Okay, so this is a very general definition of Finsler manifold.
Is it f square inside the second derivative?
Yes, yes, square.
So it's more than
Less. So less than
Why it's
convex.
f squared?
Because for Riemann manifold, this coincides with the original Riemann metric. Okay. So, okay. So,
So you're not requiring that f is a norm.
Huh?
Only that f squared is convex.
That's quite complex.
F doesn't have to be a norm. That's what you're saying.
I don't know. This is more than complex. I mean, this means that the unit sphere is positively curved. So this means so the unit sphere is something like this. So if f is 1, and then this strong convection means this is positively curved. Because this is positively hinged, so there's no fluctuation in the unit sphere. Okay, so this is stronger than usual complexity condition. And then so this GI is the important quantity because we can define. So because this is positively hinged, so this can define the inner product. So, inner product defined by this matrix is okay. So this picture we consider in the tangent space, and then this GB can be drawn like this. So we consider, for example, this is B, and then we consider normalization of B. So this point, so B of f of B, and then the unit sphere of GB is written like this. Maybe it's like this. Okay, so this is the unit sphere of GB. Okay, so because this is strongly convex, there's ellipsoid, unique ellipsoid tangent of second order. Because this is positively mixed. There's unique tangent, there's unique ellipsoid tangent of the second order. Then this ellipsoid coincides with the unit sphere of GB. In this case, and of course, if the manifold is Riemannian, all GB coincides with the original Riemann structure. okay, so now by using this f, we can define some natural geometric quantities like distance and geodesics. Distance. And the distance is defined just like in a natural way. For the points in M, the distance from x to y is just the infime of length of curves between them. And here, gamma is some curve, say u1 from x to y. And but one short remark is just this is not symmetric, so because our norm is only positively homogeneous. So this is not necessarily coincide with the xy. The yx can be defined from the xy. So in general. And then, well, I think this distance structure we can consider geodesics in the sense of metric geometry. So, yes, of course, we can also consider geodesic equation by coordinates, but finally, this differential geometry definition coincides with the metric geometric definition. So, geodesics are just locally distance minimizing curves. Curves of constant range. Constant speed.
The geodesics are now directed. Is that like they only are locally minimizing in one direction? Is that true?
Yes. So yes, only positive direction. Okay. So that now we have nice distance structure.
So this f has some negativity. I think it's like x squared minus y squared. Or it's not a metric.
I know.
No, f is positive.
Yeah, it is not negative.
F is positive.
Yeah, and I mean, actually, this non-symmetry is not so important. So
Here C is positive.
yes, but this is not really important. So if you like, we consider only symmetric norms, usual symmetric norms. And so we have distance structure, but how about measure on Finsler case? And I will explain about this later, but we don't have a measure as good as Riemannian volume measure in Finsler case. So in a sense, there's no nice measure in Finsler case in general. Measure, but there's no nice measure. In general. So then we fix just one arbitrary measure. Are able to positive and infinity measure. So I will explain about this later. Okay. So this is the best of instant geometry, and then next we want to consider Ricci curvature. And the Ricci curvature, the definition of the Ricci curvature was given many years ago by just tensor calculus. So we just fix some unit vector with unit vector, and then the Ricci curvature of B is usually defined by tensor calculus. But I don't remember the definition by tensor calculus, and it's not interesting to give the just definition by coordinates, and so I will explain useful observation of Shin. With Shin. Right now. So we start from a unit vector, and then we extend this vector to a vector field. B in such a way that all integral curves of B are geometric. And actually this is possible like this. So we fix some vector V and consider geometric passing through this point with this gamma to 0 is V. So this is geometric. And then we go back along this gamma a little, and we consider gradient vectors of geometric from this point. And then this B, this vector field satisfies this condition. And then by this vector field, in this way we can consider Riemann structure to use. And then Shin observes that the Ricci curvature of B in the Finsler setting is just the Ricci curvature of B, but with this Riemann structure G. For this Riemann. So yes, and this is very useful interpretation. Okay. So it is very useful, but for Ricci curvature, we want to control the measure, and now we fix arbitrary measure. So the Ricci curvature should be modified with respect to M. So we should modify this curvature according to M. And then we use the theory of the weighted Riemann manifold to modify this Ricci curvature one, and actually we use this kind of picture, and then we can define some modified Ricci curvature like this for one parameter n between the dimension of the manifold and infinity. We define the Ricci n, Ricci capital N of B is the Ricci of B plus the okay, maybe we should something. Okay, so we we decompose this measure m like this. So we decompose this measure m e to the minus psi times volume measure of Gb. Okay. Then each n is defined by using this psi, this weight psi, like this. So gamma square so second derivative of psi minus the square of the first derivative of psi over n, capital N minus n. So this, and for as limits we define each small m is just as a limit. So if the third term vanishes, this is well defined. If this third term vanishes, and otherwise this should be minus infinity. Otherwise it should be minus infinity. Okay, and also the infinite for infinite dimensional case. We have famous Berkeley tensor. We have the famous Berkeley tensor.
Are these what sort of object? Are these two tensors?
Two tensors?
Are they numbers? Is this a number? Like what sort of object?
Object of what?
Like because Ricci of what like are these, is Ricci of V, is that a tensor or is that a number?
It's just not number.
All right.
So it is a Ricci curvature of this vector.
And then you apply it to V again. It's like oh, I see.
Okay.
Sorry.
Thank you.
Yeah.
Okay, so and this final one is the famous Berkeley tensor. In this setting, and this final dimensional case is due to charm in the Riemann case. Okay. And here some short remarks about this. Short remarks about this. It's easy to see from the definition that Ricci curvature is monotone in M. So I mean, and this the Ricci infinity is the largest quantity. It's larger than each capital N and it's larger than each small n. Yeah. This is always true. And we will consider lower bound of Ricci curvature. So bounding Ricci infinity is easiest, and bounding is small n is most difficult. And actually, in Finsler setting, we cannot bound this Ricci m in general. So in general, there is no nice measure m such that the first derivative of psi is 0. So this means that there's no nice measure in Finsler case in general. Of course, for Riemann manifold, we can choose just Riemann volume measure and this holds, but in Finsler case, we cannot have this kind of measure in general. So this is the reason why we start with any measure m. Okay, so this is the definition of Ricci curvature, and now we know this Ricci curvature is very nice and natural quantity because, for example, we have this kind of theorem. So the lower bound of this Ricci curvature is equivalent to the curvature dimension considered to lost variance to variance curvature dimension. And it should be for parameters k and n. So k is curvature and n is dimension. So this is by itself. So this is natural quantity in this sense, and also we have first a Wolfram type formula. Formula for this kind of Ricci curvature, and also as natural applications, some gradient estimate. As an application. Okay. Okay, so this is very natural quantity, and I will explain about mainly curvature dimension constant. Curvature dimension constant because this is very beautiful theory about Ricci curvature and optional transport theory. So curvature dimension function, and for general n it's a bit complicated, so we just consider only infinite dimensions here. So and as I said, this is the weakest bound because Ricci infinity is the largest quantity. Okay, so this is due to German lot belonging. And so to explain about this, I need to say something about optional transport theory. So this is a kind of convection of some function on the space of probability measures. So PM, by PM we mean a set of probability measures. On M. And then by P2 we mean a subset with finite second moment. But here the distance is not symmetric, so we assume both distances from and to y is finite. For some or any y. Okay. Then in this space P2 we can define the Wasserstein distance. It's L2 Wasserstein distance. Maybe I'll just give a very quick definition of this. It's a kind of the least cost the least cost when one transport one measure to a different measure. So therefore, measure its Wasserstein distance is the least cost transporting mu to nu, and it's defined by sum of coupling of pi of nu and nu, and it's L2 distance. With respect to pi. So it's normal of the distance with respect to pi. And here pi is a coupling of mu and nu, so pi is a probability measure of the product space, such that its projections to each marginals are mu and nu. So then one push forward pi to the first margin, it's nu, and the second margin is nu. So the projection. And of course, for example, the product measure is always coupling of mu and nu, but in general this is not a good coupling. And we take Inchman for couplings. And actually this is distance, nice distance on the V2 space. Okay. And then the curvature dimension function is the convexity of entropy function in this space.
This distance is symmetrical, not symmetrical?
In this case, this is not symmetric. Not symmetric, because the distance is symmetric. That is we have just triangle inequality and positivity. Okay, and so we consider a function on this space. So it goes the relative entropy. And if this here is absolutely constant. This is it can be write down by using density function. No. With mu is absolutely constant. Written like this, and otherwise it's just for plus infinity. So if mu has some singular part, it's infinity. Okay, so this is the relative entropy. Yeah, and I mark that this is minus of the usual Boltzmann entropy. So if the measure revolves around heat flow, then this entropy will decrease, because this is as different sign from the Boltzmann entropy. And then the curvature dimension function. Infinity is by definition the K convexity of entropy in this Wasserstein space. So is convex in Wasserstein space, and so more precisely we have this kind of weak chain convexity condition along any Wasserstein geometry. for any Washer standard. Okay, and one geometric way to explain this thing is like this. So we consider maybe small balls in the space. If the space is positively curved, and then the logic in the virtual science space seems like this. So and the intermediate measure has much bigger support, and then bigger support means in a sense less entropy, because this is the mass of the Boltzmann entropy. And then the intermediate point has less entropy, so the entropy is more convex. And in negatively curved case, we have a different picture. So the intermediate measure is more and more concentrated. Then this has more entropy than endpoints, so the entropy it's not so convex in this case. So this is the geometric meaning of it. And also these kind of pictures can be considered as blooming of skin codes in curved spaces. Blooming inequality for curved spaces. And actually to prove the equivalence between the curvature dimension condition and Ricci curvature, we actually use like this. So the general curvature dimension condition implies blooming inequality, and blooming inequality with this kind of picture implies Ricci curvature bound, each bound, and then by each bound we have the general curvature dimension. So the blooming inequality is equivalent to the Ricci curvature bound.
Could you be more specific? Is it with dimension or with?
For any k and n we can formulate. For any k and n. We can formulate some kind of blooming inequality on curved space. Okay, so this is definition of the curvature dimension. And by this convexity, and especially for positive K, we have many nice applications. Okay, so for K positive K, the curvature dimension implies right. So for example, easy example is just a flat space, but with Gaussian method. Some kind of Gaussian method. Then it's positively curved in this sense. Okay, and then we have the total measure is finite. Because this is more complex than Gaussian, so its total mass is finite, and so we can normalize M. Normalize M. Then helps, for example, that paragraph encode. It's like so. In our case, the distance is not so symmetric. It's not symmetric. So but in any way, we can bound the virtual sign distance from mu to nu by above by over k times the entropy. Okay, and this is actually very eta is derived from the convexity. We apply just this convexity to from between mu and mu, and then we have this inequality very easy. And by a general theory, tangent inequality implies normal concentration measures. And this is also easy, but I don't have explained what it is. I don't easily implies as the normal concentration measure. So to be precise, this means we consider concentration function defined like this. So supremum of 1 minus mu of the R neighborhood of some set A, and A has at least half of the total volume. And then this can be balanced by 2 times. By tangent inequality, we can have this bound. This is not sharp under the sculpture dimension control, but we have this kind of bound. And this is also easy by applying the tangent inequality to normal distribution, uniform distribution. So on 2 sets, A and B is now M minus R neighborhood of A. So this is R neighborhood of A. In which, okay, in some distance, I don't explain what it is. But anyway, we have this kind of thing naturally. We use only triangle inequality and tangent inequality. Okay. So we have these very nice applications of the curvature dimension condition. And we also have Bochner type formula, and maybe I just give you the formula. So the Bochner formula is one of the most important formula in differential geometry, and it's about Ricci curvature and Laplacian. And in Finsler setting, the natural Laplacian should be nonlinear. So I will not explain details, but I just give the formula. So Finsler Bochner formula is so you need to define Laplacian, and it's like, oh, okay. Maybe I don't need, maybe I just give you the Laplacian, the formula. It's like this. I'm not sure I remember correctly, but it's maybe like, so this is the Laplacian, but with respect to the Riemannian structure G divided into U. so you're correct. And this is the Laplacian with respect to the Riemann structure graph view. But this is our nonlinear Laplacian. For the Finsler manifold. And the most important thing maybe this is not the same as the infinity of this Riemannian structure G of gradient G. So this is not formula for this Riemannian structure, but we can calculate in the same way as the Riemannian case. And finally, I was surprised, but finally we have this kind of thing. And so this is due to my second student. Okay, and by natural application we have gradient estimates. Of Berkeley emirate and real type. And even real type. And also real type Harnack method. In some appropriate formulation we have. We can extend these nice analytic theorems from this kind of formula. Okay, then final last limit I want to explain about connection with the geometry of Banach spaces. And so now I'm just interested in a question for what kind of spaces can be satisfied. So this curvature dimension convention can be satisfied for what kind of space? And okay. So the first question is are there any and so I'm interested in the unit spheres for normal space. Are there any reasonable interesting class of normal spaces whose unit spheres. So unit spheres should be positively curved. And so I want to have some more quantitative estimates of unit spheres satisfied. The curvature dimension convention, or even maybe for finite length with positive case. So in a sense, so I want to find some nice class whose unit sphere is positively curved in this sense. And then we have very nice application from this general theory, Ricci curvature. Okay. And then I remind you that the curvature dimension convention is equivalent to the Ricci curvature band, but the Ricci curvature band makes sense only for smooth spaces. But one useful theorem of Rothe-Güllar is that the curvature dimension convention is stable under convergence, measured from transfer convergence. So then one should check the Ricci curvature band only for smooth norms, and then by stability we can obtain the curvature dimension function for singular spaces. So we just go. Norms. And then the curvature dimension function is there. And run the measure the Gromov-Hassel conversion. So Ricci calculation concern only smooth cases. So what we have to check is this guy, this one. And then as I said, Ricci curvature is the sum of Ricci curvature plus some term coming from the weight, and so this is about metric and this is about measure, and I'm not sure what maybe this measure part is easier, and I'm not sure what this may be easier, and then for Ricci curvature part I have more concrete problem, but so do the unit spheres of two uniformly convex bar spaces are normal spaces satisfy each bound for some cos k. I believe this is true for some k depending on the modulus of convexity. So, and I just recall the definition of uniform convexity. This is useful notion in bar space. Just remind that. Convexity is just it's just convexity of the square norm. It's like some constant 1 not smaller than c not smaller than 1, and for any two vectors we have this kind of convexity. It is -4. So it's just convexity of the square norm, and so I think this implies the curvature band. And actually, if this is true, if this Q2 is true, and then this Ricci bound could imply the concentration measure, and this recovers the Gromov-Hassel theorem of the normal concentration for this kind of normal space. And also, I hope this Q1 covers much more general spaces, because each curvature band is very much weaker than this kind of convexity condition, because the Ricci curvature is the trace of sectional curvature, and the sectional curvature is the product of principal curvature. So Ricci is the trace of sectional curvature. So the curvature of this one is vector is the sum of sectional curvatures of these kind of planes. And then the sectional curvature is the product of principal curvature. And then I think that the uniform convexity it even controls this principal curvature on sphere. It controls the principal curvature, so this is very much stronger than just bounding Ricci curvature. So I hope there are some nice objects covered by Q1 but not covered by Q2. Okay. And actually I tried to solve Q2 many times but it was not successful because first I tried to calculate the Ricci curvature by using coordinates, but the calculation is very lengthy and it's not a good idea. And then maybe another way is to use this kind of picture. So I'm not sure if it's possible, but I think some technique in the geometry of Banach space is to imply the Minkowski inequality by using the two uniformly convex, and then it implies Ricci curvature. I think this is more elegant way of trying to solve Q. And if you have any idea or suggestions to please tell me about that. And I stop here.
Thank you very much. Are there any questions?
Can you give the most basic example of like a Finsler manifold, which is like not a Riemannian manifold, like just the most natural kind of basic example? Why one?
Like unit square.
Oh, so that you think that's the most natural?
Most basic. It was natural. And also in differential geometry, like Teichmüller space is complete Finsler space. I mean, with Teichmüller metric is Finsler.
Questions? Thank you again.
Thank you very much.